Let's get started. Like I said, I'm still working on exam. That out. Same with exam 1 corrections. Homework 7 is due today. How did that go? I know that was a little bit of alphabet soup, but hopefully there was like a clear target at the end of the day based on what was in the back of the book. I will tell you that homework 8.1 will be much kinder. It will probably be among the simplest homeworks that we've had in the entire semester. I would be stunned if it do it, because homework 8.1 is about that yellow box, okay? Now I'm going to go ahead and tell you, we're going to have a little bit of a derivation today, and today's going to get a little bit more generalized and a little bit more abstract, but in the end it's going to lead to that. A very, very plug and chug expression to perform what is called a stress transformation, okay? And stress transformation is all about generalizing the problem associated with stress analysis. This entire class up until now has been taking fundamental stress cases one at a time and knocking them out. So axial loads. So if I have a bar subjected to an axial load, I know how to compute the stress, I know how to compute the strain, the deformation, and any which way in between. Same thing with torsion, okay? Same thing with bending, with shear. We've handled all of those fundamental cases. But what about all the other cases? What about all the other things that we could deal with as engineers? So I want to talk about the motivation for what I'm calling stress analysis. And I'll give you sort of like two ideas to chew on, okay? Let me just, and you don't have to write this down, but this will kind of give you an idea, okay? So here's an idea to think about, okay? Let's say I have a bar and a yank on it. That should be a problem that we conceptually can handle in this class, right? Or as engineers, right? We know what stress is P over A, strain, deformation, etc. But what if I take that bar and I also twist it? What if I also put loads on it? What if I do all that stuff at the same time? Okay? What that means is I'm going to get a bunch of stresses all at the same time. I'm going to get a bunch of different normal stresses, a bunch of different shear stresses, right? Now, I could keep this simple, and I could say, all right, take my normal stresses as just the sum of all the individual normal stresses, and the shear stresses as the sum of all the individual shear stresses. And that's fine, okay? But there is a question that I want you to think about in this lecture, and that's, what about orientation? And that probably doesn't mean a lot right now. That doesn't make a lot of sense, but that will here in a little bit, okay? Getting at, though, I'll say this, what I'm ultimately getting at in terms of orientation is that whenever we've done stress analysis problems up until explicitly defined our problems based on a chosen coordinate system. So that might be the x-axis and that might be the y-axis. And we've kind of done that because it makes the math simpler, it makes it a little easier to understand. But that is a coordinate system we as the analyst chose, right? Orientation, that frame of reference. There's a quote from Neil deGrasse Tyson. He says, the universe is under no obligation to make sense to you, right? Just as worst case scenarios are under no obligation to fit some pretty coordinate system, right? And that seems like kind of an abstract idea. I'm going to give you some concrete examples of it here in a little bit. But that's one motivation for looking at stress analysis. Here's another. We've been looking at fundamental cases, axial loads, beams, torsion, etc. And to be clear, more often than not, we as engineers try to employ those in engineering applications because they're well understood, they're well known. We are responsible for designing systems that need to maintain the safety, health, and welfare of the public. So if we're going to use some thinking outside of the box, we need to make sure that it's going to behave accordingly. But every now and then, the situation necessitates something odd, some odd geometry, some odd loading, some odd configuration. So let's say you have some, random shape that's subjected to all sorts of loads. We have a load here, we have a load here, we have a load here, a moment here, a load here, etc. Some random body where these pretty little P over A formulas and sigma equals my over I, they don't quite work, okay? So how do we handle this in the real world? Well, the way that we handle it is with things like NX, Abacus, ANSYS, etc. Right? There's software out there that will perform stress analysis for odd geometries. But understanding what it's doing and understanding a little bit about the math that it does in the background is going to make you a better engineer. Because in addition to just performing a straight finite element analysis, there is a series of stress analysis computations that it's doing that you might not have been exposed to. I'm curious, you might have done some stress analysis in Engineering 102 with NX. How many, did y'all do that in 102? I'm just curious. You might have, might not. You'll kind of see what I'm talking about. Breaking this down. Let's go back to basics, okay? Following beam, we have our secret weapons of engineering, the samurai sword or the lightsaber if you happen to be a sci-fi fan, okay? Now, here's the beam. I cut that beam like so, okay? And I split that beam into separate components, right? I've used the example before in class that if I'm sitting here on this table and somebody takes a samurai sword or a lightsaber through the table over here, I'm going to fall down, right? The reason why is because inside this point right here at the table, there's an unknown force in the x direction, unknown force in the y direction, unknown moment that's maintaining equilibrium. Once you cut the section, you remove from the structure the ability to maintain equilibrium. So it's an analytical tool to determine those internal forces. But here's the thing, we've kind of been using this like a hacksaw and not like a scalpel. Let me ask you a question, okay? Here's cutting a section like this. Angle. What if I change the orientation? What if I change my frame of reference? Instead of cutting it according to some coordinate system, political perspective, what if I cut it at an arc? Well, it stands to reason, if we do it like this, we're going to get different stresses, right? So any angled cut would result in a different area, right? Just bare minimum, right? If sigma equals P over A, that cut has a different area than this one. So we're going to get different stresses there. Any angled cut would take forces and split them into normal and tangential components. So we're going to get different forces and different areas. So it stands to reason we're going to get different stresses. And maybe a more reasonable question to ask would be, which is the worst way? What's the worst orientation that's going to generate worst case stresses? And that's kind of what I want you to think about today. Now, if you're wondering, does this happen in the real world or is this applicable to real engineering? You bet. And I threw some examples of here of that you would see in the three majors associated in this room. We have here a slope stability analysis for you civil engineers in the room, looking at the soil stresses under a foundation load. We have some associated biomedical engineers. We have the stresses on the segment of on the hinge of a jaw of a given patient. Okay, and what you're seeing here is what's called stress contour. Okay, so finite element analysis 101. The way that finite element analysis works is it's a technique that's utilized to perform, among many other things, but first and foremost, it is used to perform stress analysis of odd and unique situations. And basically the way that it works is we take a given component or a given system and we discretize it into a series of discrete regions that we call elements. And we assume what the solution looks like across those elements. And so the more elements we use, the better the answer we get. So there's a whole body of research focused on taking complex scenarios and applying finite element analysis techniques to determine worst case stresses and worst case scenarios. But again, even under these types of modeling conditions, it's still a human being generating the analysis. So if I was, let's say, a student in Engineering 102, and I needed to create, let's say, this machine part in NX or AutoCAD Inventor or whatever, I imagine that while you may or may not have done a stress analysis like this, in terms of crafting a part like this, you've done stuff like this in Engineering 102. Is that a fair statement? It might not have been this complicated, but you have built 3D parts and widgets and gizmos in CAD software before, at least for you mechanical engineers. Well, what we would do as stress analysts is we'd say, okay, here's this part. Let's apply a fixed or simple boundary condition here. Let's put a load. Okay. But again, it doesn't answer the question of what's the worst case scenario. For example, you see these like von Mises stresses, and you see all these different stress configurations. What they're looking at is different stress orientations. And so I kind of want to show you a little bit of what's happening under the hood, but also some techniques that we can apply using pencil and paper to generate worst case scenarios. Let me give you kind of an idea of what's going on. So we're going to kind of abstract the problem a little bit. We're going to look at a more generalized approach. So what we're going to do, given location in a system, and what I mean by a given location, so to keep it simple, let's say we have a beam simply supported, so here's the beam, we have loads on the top. We'll pick a given point, let's say that point right there on the beam. And we will, for that point, compute what's called a stress state. So we'll basically try and summarize all of the different stresses that are acting on that point at a given point, right? So, for example, in 3 dimensions, we might have a normal stress in the x direction, normal stress in the y direction, normal stress in the z direction, and then we have shear stresses across the given faces. Okay, in 3D, we have a total of 6 possible stresses: 3 normal stresses, 3 shear stresses. Okay. Now, in most situations, what we as engineers try and do whenever possible is we try and limit things to 2D. 2D is a little bit more manageable, a little bit more easy to deal with. So in 3 dimensions, we only have 3 stresses to consider: 2 normal stresses and 1 shear. And we'll talk about why that is here in a little bit. And so the question might be, instead of, so to try and frame our problem that we're looking at for a given stress state, so let's say I've computed a given stress state, what if I rotate my coordinate system? If I rotate my coordinate system, what's the new stress state? And this probably looks ridiculously complicated, okay? How do I go from this to this? And there is a simple answer. It's just trig. It's all it is. It's just trigonometry. This problem of changing orientations is one that we as engineers and scientists have known how to do for a long time. How do you think Mario jumps from one end of the screen to the other? It's all linear transformations, okay? So this is something that's actually very achievable to do, and actually comes. It's just a lot of trig. But then the obvious question would be, what's the worst case scenario? Okay? So let me kind of show you what happens in the real world. So this is a problem that we will be able to do by the end of this lecture. So I'm going to give you a given stress state like this. So let's say the x-axis stress is 30 KSI, 30 MPa. The y-axis normal stress is 50 MPa. So if I look at this stress state right here, I find a sigma max of 50 MPa, right? Because there's 2 of them, and 50 is the biggest. And I have a maximum shear stress of 40 MPa. Now, I propose what happens is let's take this and let's rotate it 20 degrees. Okay? And I'm going to get new stresses. Now, if you're wondering, how do I do that? How do I go from here to here? The answer is that box on slide 1. I said we're all getting to that box. Boom. Take these values, plug it into the box. Boom. We're going to show you how you get that box here in a little bit. But boom, this is what you get. Now, let's look at this stress state. What's sigma max here? Well, sigma max here, if I look at the orange arrows, the normal ones, sigma x or sigma max is 56.5. Tau max is 47.2. So if I, as the engineer, was designing this gizmo or this widget, and I was just using stresses and I didn't account for orientation, what would happen? Remember, the question I asked you on day 1, if I'm designing some gizmo, right? If I'm designing some gizmo, here's the gizmo, and it is holding a weight, right? And here's the puppy, right? And I designed for this, and is actually experiencing this, that could be a bad day for the puppy, right? So far? So I want you to kind of understand the motivation. That is horrible artwork, by the way. I will be the first person to admit it. What's that?
It is turtle.
So it's a cat or a turtle? Is that some long legs for that turtle. It's good that we've got some laughter at 8 o'clock in the morning. All right. So the point I'm making is that when you rotate from one stress state to another, some stresses may go up, some stresses may go down. Like we went from 50 and 30 to 25.1 and 56.5. So some increase, some decrease. But the again, when I look here, what observations could be made about the maximum? Well, we went from here to the worst case stress state. So here's a conceptual procedure to just sort of frame the next few lectures. So first, the idea is to compute the stresses according to a given coordinate system. That is something that we should be able to do right now using axial formulas, torsion. So when I say according to a given coordinate system, we're talking about P over A, TR over J, MY over I. You know, the stuff that we know how to do already. Okay? And so that might be one option. Another option is we model it in some software like NX or ANSYS or Abacus or FEMAP or what have you. Okay? So once we have a stress state, we need to develop a means of transforming that stress state, going from this to this. And it's all about changing orientation, changing angles. And so once we understand that, I think we know where this is going. The third is, what's the worst case orientation? What's the worst case stresses that we would see? And we have a term for those. We call those the principal stresses. Okay? Now, to do all of this, to get from point A to point B is going to require a lot of trig and some calculus. Okay? But what we're going to find out after a couple of years is that we're going to develop an incredibly simple graphical shortcut for doing this. And the name of that graphical shortcut is called Mohr circle. Okay, I know there might be a couple biomedical in one class or another, but that's what Mohr circle is. It's just a conceptual and a graphical shortcut for doing a lot of this. Now, if you're wondering, what does circles have to do with all of this? Let's go back to trig. Okay, I've heard, if you ask somebody what trig is and they say it's the study of triangles, I go, no, that's not enough. Okay, I would argue that trig is the connection of three fundamental ideas. Now, the first is solving a right triangle, right? And we can take that and extend it to solving for any arbitrary triangle using law of sines and law of cosines. But yeah, we start with solving triangles, right? So given three pieces of data, what's the remaining data to solve the triangle? And so we develop our SOHCAHTOA, sine, cosine, tangent, what have you. And then we're mathematicians at some point before we become engineers and get wise to the ways of the world. And we say, okay, let's take these trigonometric functions and let's start graphing them. And we go, okay, here's some interesting trends. So for example, when the sine is maximized, cosine is 0. It's almost like the derivative of the sine is the cosine. And so we start to learn these patterns associated with sines and cosines, and then we go, wait a minute. The sine and cosine, all the sine and cosine are the x and y coordinates on the unit circle, right? And we find the same patterns. For example, here's the circle, right? When the x coordinate is maximized, it's 0. It's almost like when x is maximized, y is 0. It's almost like with the y, when the y is maximized, x is 0. The sine is maximized, x is 0. Circles, but that's probably getting a little bit too abstract for 8:15 in the morning. Now, we're going to have a derivation coming up, and I don't want you to forget those pesky trig ideas. You have the sine of 2 theta is 2 times the sine theta cosine theta. Remember all those things? In the morning, you're really making us remember all this stuff. No, I'm not going to make you remember it, but I am going to start pulling some of these out of the woodwork when we start looking at this derivation that we do here in a little bit. And what is going to be most useful are the double angle identities. The idea that the sine of 2 theta is 2 sine theta cosine theta. The cosine of 2 theta is 1 minus 2 sine squared theta. You remember, I know you've seen these before, right? I know it's probably been a while, but you've seen them. We are going to break them out. And the reason why the identities are useful is because we're going to start computing a lot of different stresses, and we're going to find that we can collapse everything into sines of 2 theta and cosines of 2 theta. So it's going to make the formulas maybe a little neater at the end of the day. Okay, now, we'll stop for a second, see if anybody has any questions about the concepts, because I actually want to figure out how we're going to get from these ideas to that. That's what I want to figure out. But before we do that, getting way ahead. That's way too ahead. All right. Any questions? This derivation, I've sort of split it up into 2 parts, okay? Because I want to take it one step at a time. I want to make sure a single normal stress, okay? And again, it's just trig. All right, so let's start off with a simple case. All right, note I've got the x-axis and the y-axis here, and we're going to yank on this with a single axial load P. So if I cut a section, some forces, I find that the internal axial force inside that bar is P, right? And so I take that axial force, I can determine P over A, so on and so forth. With me so far? Okay. Now, what I'm going to do is I'm going to take this section and I'm now going to cut it at some angle. All right, we'll call that angle theta, which, by the way, this derivation's on Blackboard, so if you skip, I mean, it's all here. I'm not going to make you repeat this. This is not going to be like the last homework where you have to rederive all this. So don't worry, that's okay. All right, so now I propose that, okay, if I have a perpendicular cut, if I sum forces, I'm just going to have an axial force. But if I cut at an angle, I'm going to split that into some normal and tangential components. So I'm calling that a normal force and a shear force. Okay? So let's see if we can figure out what those are. Okay? Now you know me, I like to take forces and split them up into their x and y components. So let's take that normal force and let's split it up into components. So the x component's the cosine of theta, y component's the sine of theta. Now for 90 degrees, so the trig functions are flipped. X-axis has the sine and y-axis is the cosine. That's because the force is off 90 degrees, so we're flipping our trig functions. With me so far? So now I'm going to take some of that useful knowledge I learned in Engineering 213, and I'm going to sum forces in the x direction, I'm going to sum forces in the y direction, and I'm going to say, all right, I've got some forces in the x direction, I got a p going to the left, I got an n cosine theta going to the right, and a b sine theta going to the left, and I get an equation. Then I sum forces in the y direction, that going up, that going up. They have to add up to be 0, just as the sum forces in the x direction do. And then I look at those 2 boxes, and I got 2 equations, 2 unknowns. Remember we broke out, we had problems like that in statics, and we broke out the Casio FX 115 ES Plus, and we used our 2x2 equation solver, right? So we can use a similar approach to solve these 2 equations, and this is what we get. We get that n is p cosine theta, and v is negative p sine theta. Now, you might, does that work? Well, let's see. What happens if the angle is 0 degrees? Well, if the angle is 0 degrees, that's p, and that's 0. But 0 degrees corresponds to a cut like this. And if we're cutting at 90 degrees, we shouldn't get any shear force, right? The only reason that we're getting this v force is because sure everybody's good with that. Everybody good with that so far? Okay. This is sum of forces, sum of forces. We need stresses. Well, how do we determine stresses with forces? We take force over area. Here, I'm going to call this A naught, and we'll call this AT, right? So some area A naught, AT, is the area divided by the cosine. The area is going to get bigger as we we make that cut. So I'm going to take these and I'm going to divide them by the areas. Now, before I do that, I'm going to introduce some terminology. So I want to make sure everybody's following along with So whenever we do stress transformations, a little different than your textbooks, but I think this is a little easier to follow. So what we'll have is, I'm going to call X and Y my original coordinate system, and I'm going to call 1 and 2 my new coordinate system, right? So this is X and Y, that's 1 and 2, okay? So if I say sigma sub X, what I'm referring to is the normal stress in the direction of the X-axis, whereas if I say sigma 1, I'm referring to the normal stress along the 1 axis, right? So if I had, so to introduce the notation, tau 1, 2 is a shear stress, that would be perpendicular to the first axis, parallel to the second axis, okay? But to be clear, the order of the shear subscripts doesn't matter a whole lot, and that'll become clear here in a little bit. So here's my stresses, right? So if sigma X is just P over A, sigma 1 is N over AT. All right, so this is where the trick kind of follows. Okay, so sigma 1 is N over AT. So N over AT. AT is A naught divided by the cosine, and N is P cosine theta. So I can relate the stress from this to the stress from this, 1 is sigma X times the cosine squared. For the shear stress, I'm going to take the shear load divided by the area. So I've got negative P sine theta. The area is A naught cosine theta. Plug and chug. I have a P over A, so that's sigma theta times cosine theta, because I have fraction dividing, so flip and multiply. Just make sure the concepts kind of make sense on that. I'm going to let everybody sort of soak that in a little bit. Now this is a very hopeful point in the derivation, because I'm basically saying at this point that I know I can deal with stresses directly, but from here on out, I shouldn't need to go back to equilibrium every time I do a stress transformation, because I have sigma 1 equals the original stress times trick. Okay, so I don't have to go back to equilibrium anymore, and that's going to make moving forward, hopefully, a lot simpler. All right. Everybody good? Okay. Now, if you notice, I have these cosine squareds and these sine cosine. If you look at these terms, I actually relate a lot of this to my double angle identities. So these blue boxes are some double angle identities that I would utilize in my derivation. So instead of cosine squared, I'm going to say 1 plus cosine 2 theta over 2. Instead of sine theta cosine theta, because this is 2 sine cosine, I'll just divide by 2 and I'll do this. Okay? There is another reason why I'm utilizing 2 thetas, and 2 thetas, the reason for that will become very, very important when we look at Moore's circle. Because with Moore's circle, if you have Moore's circle drawn and you want to know a rotated stress state, you have to incorporate 2 theta. So it's sort of baked into the analysis that we do with Moore's circle. So far, so good? Okay. So I want to summarize the derivation so far. So I want to make the following statement and make sure that we're clear on it. If we have an element that is subjected to some stress along the x-axis, I generate the following stresses in the 1, 2 coordinate system. So sigma x will become sigma 1 and tau 1, 2. And in order to compute those, we take sigma x times some trig. Sigma x times some trig. So now what I want to do is I want to take this and generalize stress at a time. Now I want to take this and extend it to a bunch of other stresses. So I want to more formally discuss these stress states, and I want to look at not just transforming a single stress, but all the stresses. Okay? So we can do the same types of transformation for sigma x as we do for sigma y, tau xy, we can even extend it into 3D, but we need to discuss states of stress. And so we're going to have problems, we've already had problems that have a normal stress, a shear stress. We're going to have situations where we have multiple stresses. Hell, we've already had one when we looked at beams. If I pick an arbitrary point in a beam, it has a normal stress and a shear stress. It already has multiple stresses going on at a single point, okay? We're going to have some very specific applications coming later. For example, pressure vessels. We're going to talk about pressure vessels a little later. That is a very specific application of a problem with multiple stresses, okay? And so we need to discuss states of stress. So if we investigate some point in a body, and the idea is that we look at the point as some differential element, right? So the idea is the element is dxy and maybe dy tall. And so if we were doing this in 3D, it would be dz thick, something like that. And so it's like a point, but we sort of idealize it as either a square or a cube with a differential thickness and width and height. So I propose that, okay, we're looking at a situation where we could have at most 4 stresses. 2 normal components and 2 shear components, right? So, for example, this is a stress. Notice how if I look at this first stress right here, they have to be equal and opposite. They have to be equal and opposite for equilibrium to be maintained, right? And I've drawn them according to their accepted positive sign convention. So we consider tensile stresses to be positive, right? Similarly with y, a stress going up and a stress going down. Those are my 2 normal stress components. Now likewise, we have 2 shear stress components. We could call them tau xy and tau yx. So those are the 4 possible stresses. Well, actually there's always 3 stresses. Because if you look at your shear stresses, it is actually very easy to show that the 2 shear stresses have to be equal, okay? And we can look at this actually very easy. So first off, if we look these stresses over here, they are not, right? So if I look at these stresses right here, these are not in equilibrium. Why are they not in equilibrium? Well, same stress going up equals the same stress going down, but this wants to rotate the section, right? It is a stress couple, right? One's going up, one's going down. They're parallel, separated by a moment arm, right? So they're wanting to rotate, right? But here's the thing. If these stresses are wanting to rotate this way, these stresses down here are wanting to rotate the other direction. And the only way that they can maintain moment equilibrium is if they're the same, right? That's a pretty trivial proof that your shear stresses are equal. That's why I say, it's really not all that important to get all worked up about the subscripts, like tau xy and tau yx, which direction. They're all the same. If you're wanting to draw your stress state and you want a shortcut for ensuring that you've done it right, here's Dr. Mike's shortcut. You're trying to figure out positive shear stresses. Look at the top. If it's a positive shear stress, it should go to the right. And past that, all the arrow tips have to be one another. So, for example, if I give you tau x, y is 20, right? Here's how you would represent it. The arrow on the right goes up, which means that goes like that, and then the arrow tips touch one another, right? So negative 20 would just be in the opposite direction. Okay, don't worry, we'll have an example on that. Okay. Sigma 2, a tau 1, 2, etc. So, this is actually me skipping a lot of math. So, in that red box, that's what we've already done. We just did that in the past few slides. Sigma 1 equals sigma x times some trig. Tau 1, 2 is sigma x times some trig. So I did the derivation for sigma x. If you are happy to do the derivation for sigma y and tau xy, or you could sort of just trust me that these are right. You tell me. Can we do it? These are correct. Now, so we now have an expression that can rotate sigma x to a new coordinate system, sigma y to a new coordinate system, and tau xy to a new coordinate system. So all I have to do is collect that and simplify. Now, an astute observer would look at this previous. Very easily derive sigma 2 by just replacing theta with theta equals 90 degrees and just doing all the trick. So, the equations for stress transformation are as follows. So, if I have a given stress state, so the idea is if I have this, sigma x, sigma y, tau xy, if I have this data, and I would like to turn it into this data, I need a transformation. This is that transformation. This might be nudge, nudge, wink, wink. I'll give everybody a sec to write that down. Now, I use 1 and 2. Your textbook uses x sub 1 and y sub 1. Honestly, I think it's kind of cluttered, so I just use 1 and 2. So. Get a sec to copy that down, and then we're going to do one. Again, one of the things I wanted to be crystal clear about is that I think that the idea surrounding stress transformations and Mohr circle is, the first time you hear it, a little hard to grasp. But in practice, boy, it's easy. It's very easy to do. I'm telling you, this is probably one of the easiest homework assignments we're going to have in this class. So. All right, has everybody got this? So let's look at an example. Okay, so after analyzing a structure, we have some stress state. We know that sigma x is plus 10, sigma y is negative 10, and tau xy is negative 5. Okay, I want to determine the new stress state along this coordinate system. Okay, let me pull up the notebook. I already have this copied on there. We will check this out. Again, this is really going to be a formality. It's a very, very short example. I'm going to make you draw the before and after on your homework. So. Do is we need to determine the orientation, or specifically the orientation angle, theta. And I'm going to say that, you know how in the past I have used sort of the analogy that, hey, why use angles when you can use slope ratios? But with this, I'm going to say, you know what? Let's just use the angles. So ultimately what I'm interested in is this angle right here. I'm interested in that angle, right? Because we're going from this to that. So I'm interested in that angle. That's the angle I'm interested in. So all we have to do is we have to say, all right, here's that. We're given that this is 3 and that's 4. We need an angle, right? I propose that the angle is the inverse tangent of opposite over adjacent. And what is that in angles? Or in angles. In degrees. We'll say 2 decimal places. And I'll say this, I don't really care if you do degrees or radians, but I think it's kind of easier to deal with degrees with this. So 2 decimal places. 53.13. All right. Second. All right. Now, because all of our expressions utilize 2 theta, I'm going to go ahead and do 2 theta right now and say it's 106.26 degrees. I'm just going to go ahead and do that now. I trust me, I think it's okay. What's that? There you go, exactly. So let's do sigma 1. Sigma 1 is, and honestly, I kind of have to write these down myself. I can never remember them right off the top of my head. Like, I know what they look like, but every now and then I'll get a sign wrong. Sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. Okay, and I put them up. They're on the upper part of the screen, but sigma x is plus 6, sigma y is minus 10, and tau xy is minus 5. By the way, one of the nice things about stress transformation is that they are very kind to you from a units perspective. Once you get them all in consistent units, they're all we're going to skip right in the units for this. So 6 minus 10 over 2 plus 6 plus 10 over 2 cosine 106.26 degrees plus negative 5. Here, I'll just say minus 5. Minus 5 sine 106.26 degrees. So, what do we get? We'll say 2 decimal places. That's enough to sort of make a point. Well, what do we get? Oh, you're sitting there shaking your head no. I didn't get that.
Negative 9.0.
That's what I got. That's what I got. Negative 9.04 KSI. All right. So sigma 2. Okay, so sigma 1 and sigma 2 have very similar formulas. Sigma 2 is sigma x minus sigma y over 2. And then this term is minus on the outside. That's minus as well. So does somebody have an answer for this one? Well, Jared could be the second. I want to see if somebody else can get this one. I'm not going to plug it. I'll let everybody, the values are there, so.
You know what? Gotta do a nice thing because somebody doesn't own a calculator here.
Hey, you can second it.
More about you than it is about me.
minus y. It is, but y was negative.
Okay,
Yeah.
thank you. That's
Yeah. Yeah. Maybe I skipped that. Maybe I should have. That was me kind of doing some shortcuts.
You're good.
This one. 15.04. I got 5.04. Anybody else? Plus 5.04. Or did I get? Or did you get 15?
I also got 15.
All right. Maybe it was 15. Hold on. Let's see. Hold on. Did I bring my T89? I did.
You already got that too.
All right. Let's see. Well, you know what? I'm just gonna believe. Let's just believe. This is me believing you. All right. Let me make sure I write my signs.
Jared got the 5. That's what I was.
What's that?
Jared got the 5 as well.
Okay. You got the 15?
No, he got the 5.
You got 5.04.
Jared also got.
Hold on. Hold on. Okay. All right. This is 6 plus 10 over 2 minus 6 plus 10 over 2 cosine. This is plus 5 sine 106.26. Or 1, sorry. Hold on. Yeah, we gotta sort this out. But it's 6.
It's 6 minus.
Alright. Yeah, because over here, this is 6 minus negative 10. Right? Hold on.
I think the original equation has a plus
Yeah, that,
there.
yeah.
Oh, is that, see, again, this is probably what it is. So this has a plus here, so this is, okay. Yeah, I told you, like, it was going off memory. Alright, hold on. I even brought my textbook. We're gonna make sure I got this right. Maybe they gave me decaf this morning. Let's see. Hold on, let's see. Yeah, you're right. That's supposed to have a plus. You're right. But it is 5, right? Yeah, I think I know what I did. Yeah, I know what I did. I put a plus where a minus, or a minus where a plus should go. Yeah. So that's correct. Oh, the distraction about the turtle. 1, 2. Okay. Now this one I'm almost positive I got right. So this one's negative sigma x minus sigma y over 2. This one's a little different. So this is sine 2 theta plus tau xy cosine 2 theta. While you all are computing that, I'm gonna make sure that is right, isn't it? Yes, that's right. What about this? Okay, all right. That's what I got. All right. We'll add 0.25 to the mistake count for that. Let's just sort of recap. Hold on. So we had sigma x was plus 6, sigma y is minus 10, and tau xy is minus 5. Now, the way that you would draw this, it's already drawn up top, but the way that you would draw this is like this. So here's our stress block. Here, let me move that down a little bit. So sigma x is positive. So that's in tension. Sigma y is negative. So that's in compression. And then for the shear is negative. So I draw the top to the left. And if I draw the top to the left, the bottom needs to go to the right. And make sure on the other side that the arrows point towards one another. So that's 5. And then rotated, we got sigma 1 is negative 9.04. Sigma 2 is positive 5.04. And then tau 1, 2 is negative 6.28. So the way that you would draw that is first off, you are drawing your box like this, right? Where this angle is 53.13 degrees. And then sigma 1 is in compression. Sigma 2 is in tension. And again, the shear is negative. So on the top left, bottom right, arrows face towards one another. So we'll say call it, but hold on. But before we do, anybody have any questions? I want to show you something. So, right? I want to look at this. This is this problem we just did, done doing the transformations. So, what do I mean? Look at this. So the blue is the normal. That's 6. This minus 10, that's minus 5, right? Now what happens if we rotate it at an angle of 53.13 degrees? What do we get for sigma 1? Negative 9.04 plus 5.04, negative 6.28. It's almost like all we're doing is we're looking at the trig functions and going, what's the trig function's yield at some given angle, right? Simple, right? Okay? With me so far? So, now here's the thing to wrap your head around. We as designers are interested in what? Worst case scenarios, maximum stresses. So, what's interesting is what's going on right here. So let's look at that line. That's kind of an interesting line because we have maximum normal stresses. Maximum, like they're maximized, but what's the shear stress? 0. It's interesting. So the shear stress is minimized when the normal stresses are maximized, right? Huh. Remember a trig plot where that happens. Isn't it a circle? Technique that we can use to avoid all these complicated equations, right? The ones that we keep messing up. Maybe this on a circular plane, maybe we'll plot the normal stresses on the x-axis and the shear stresses on the y-axis. That's more circle. Now, I cannot help but show you this animation because it is just infinitely better than anything that I could that I could program. I just don't have time, but this is really great. This is really great. I'm actually going to pause the recording so I don't get some copyright strike when I put it on YouTube.